Now, one thing you may be wondering about, or if you're not wondering yet, you may start wondering about it the first time you have to do it, is how you go from a vector expressed in terms of IJK notation back into having the vector's full magnitude and direction. Well, you do it the same way that you would with when we were drawing the unit vector, or excuse me, when we were drawing the component vectors as lines and making a triangle. You use Pythagorean theorem in sine, cosine, and tangent, at least in 2 dimensions. That is, if you, for example, had a vector represented as 3i hat plus 4j hat, don't forget that that's simply 3 here, 4 here, and the way you would find that magnitude is to use the Pythagorean theorem, 3 squared plus 4 squared. Of course, if you remember your Pythagorean triples, that equals 5 squared. But you don't need to actually sketch this out if you just keep in mind that the magnitude of any vector, which is sometimes notated with bars around the name of the vector. So this is sometimes a term that's used to represent the magnitude of vector A, is found by taking vector A's x component, if it has one, squared, plus its y component, if it has one, squared, plus its z component, if it has one, squared, and take the square root of all that. Notice that if there's no z component, this is the Pythagorean theorem. A squared plus b squared equals c squared, side, side, hypotenuse. However, it turns out that the Pythagorean theorem is a special case, but this works in any number of dimensions so long as the dimensions are all orthogonal, that is perpendicular to each other, like x, y, and z are. So for a 3-dimensional vector, you can find the magnitude just as easily by taking the square root of each of the components squared and added together. In fact, if you're working with more than 3 orthogonal dimensions, which would not be the case for, moving in regular space, but if you were doing quantum mechanics or something like that, you may have any number of orthogonal dimensions. This still works. If you had a 7-dimensional vector and you wanted to know its magnitude, you would square each of the 7 components, add them together, take the square root. So how this would apply right here, like I said, this part is familiar. The magnitude of vector A would be the square root of 3 squared plus 4 squared. Of course, 3 squared is 9, 4 squared is 16. Add them together, you get 25. And so the magnitude of A, vector A, is the square root of 25, or 5 units. But like I said, it works the same way in 3 dimensions. The magnitude of vector B is going to be the square root of, now remember, just the I hat hanging out by itself really means this is just 1 times I hat. It's just we don't normally write 1 times something, since 1 times something is just the something. But I hat hanging out by itself just means that component's magnitude is 1. Also note that we're adding together the components squared. So even though the j component is -2, after we square that, that's going to become +4, because a negative times a negative is a positive. So make sure you don't write 1 squared minus 2 squared. If you were to type that into a calculator, it assumes you understand the difference between this, and this. These are 2 different things by kind of the rules of math, and so don't go typing this into your calculator if what you mean is for this to happen. Or, just an easy rule of thumb, when you're coming up with these magnitudes, you could just ignore the negatives, because 2 squared is 4, and -2 squared is 4, and so on and so forth. And then the last one over here, again, k hanging out by itself means that there's a little 1 right beside it, and so the magnitude of vector B here would be the square root of 1 squared is 1, -2 squared is 4, 1 squared is 1. 1 plus 4 plus 1 is 6. The square root is 6. I used to know about what the square root of 6 was off the top of my head. Obviously, it's more than 2, because 6 is more than 4. And it's got to be less than 3, because 9 would be 3 squared. So somewhere between 2 and 3, probably closer to the 2 side than the 3 side. I'm going to just completely make something up and call it about 2.3, but that's very rough, so don't quote me on that. But that's how the process would be to come up with the magnitude of a vector. If you wanted the direction of the vector in 2 dimensions, you could get the angle relatively simply by just using the inverse tangent of 4 over 3 if you wanted it relative to the x-axis. In 3 dimensions, it's not really nearly as convenient to talk about direction in terms of one angle. In fact, you can't talk about it in terms of one angle. That one angle and magnitude is basically what we call polar coordinates, which is a 2-dimensional type of coordinate system. In 3 dimensions, you would need either cylindrical coordinates or spherical coordinates, which means you need multiple terms to designate a particular direction, which is enough of a hassle that for a 3-dimensional vector, we generally wouldn't talk about the direction as being in terms of some particular angle. We would instead just have the direction be represented by the fact that we have how far it is in the x, how far it is in the y, how far it is in the z. You can get the individual directions there. But if you did want to talk about the direction of a vector in any number of dimensions, not just 3 dimensions, there's another way to do it, and it's that, actually, I'm going to rewrite that off to the side here. That was 3i hat plus 4j hat, because it's a good one to do a demonstration with.